In our earlier lectures, we have studied the generation of waves by electron beams in plasmas. We studied the generation of plasma wave by an electron beam via a process called true stream instability. Then we also studied generation of electromagnetic waves by two processes. One is called Cherenkov free electron laser, in which the electron beam generates a slow wave by a direct interaction, and then we discussed the device called free electron laser, where an electron beam generates a fast wave that moves faster than the beam, but the presence of a magnetic wiggler provides phase synchronism, and that gives rise to growth of waves. We also discussed the effect of tapering that can lead to efficiency enhancement for radiation generation. However, in plasmas, whenever an electron beam travels, it is always an issue to examine the stability of the beam or the plasma to filamentation. Is the beam going to maintain its uniformity of current density, or is it going to filament or fragment itself into small filaments, current filaments? And today I am going to discuss that instability, which was discovered by Weibel in 50s and is given a name Weibel instability. So today I will discuss what is a counter streaming beam plasma system. Then we will discuss the physical mechanism of growth of a magnetic perturbation. We will carry out a instability analysis, drive a dispersion relation, and make some assessment of saturation of the instability, and see, if time permits, are there some other mechanisms of self generated magnetic fields. Well, before I go into the analysis of true stream instability, I would like to mention a few things about beam plasma system. In a beam plasma system, whenever you have, suppose, a chamber here and launch an electron beam, as the beam enters there, then in the beam illuminated region, momentarily the space charge becomes negative, because if the plasma earlier had equal density of negative charge and positive charge of the ion, but when the additional beam electrons arrive here, then the charge becomes negative. However, in a very short while, that negative space charge that is created here will repel the plasma electrons outward. It will also repel the beam electrons, but because the beam electrons are travelling with a large velocity, large inertia they have, and consequently their departure from this region to outside is negligible. But the plasma electrons, which are not moving with any average velocity, they move out, and you get some sort of a space charge neutralized system. This is called space charge neutralization of the beam. What also happens is that when the beam is launched, it creates a magnetic field in the system, and as the magnetic field evolves with the arrival of the beam, it produces a back EMF that produces a return current, and plasma electrons carry a current in the opposite direction. So, we often encounter a system in which beam current is in the forward direction and plasma current is in the reverse direction. Obviously, if the two currents are of equal value and they counter each other, then the net current in the system is 0, and the beam propagation is termed as propagation under current neutralization. And if you can achieve that situation in which the beam current and plasma current are exactly cancelling each other, then there is no magnetic field in the system. However, is it possible that the two currents really do not overlap. They may overlap in the beginning, but if there is a small perturbation in the system that makes the two currents deviate from each other, so there is no exact overlap, then there is a possibility of net current being finite and a magnetic field being generated. I think we are aware of the fact that if I have a current carrying wire, it produces a magnetic field of this sort, azimuthal magnetic field around this current carrying wire. And if I have another current carrying wire carrying current in the opposite direction, then the magnetic field will be of opposite nature. So, in the intermediate region, the two magnetic fields will add if there are currents in the opposite directions. So, if I consider an electron beam, suppose this is my electron beam travelling in this direction, and my plasma current is in this direction, interpenetrating, uniformly interpenetrating, and there is no net current in the system. Suppose I have a system like this, and if I consider a small magnetic perturbation, suppose I have a magnetic field which is in one direction and in the opposite direction here, in one direction, opposite direction, perpendicular to the plane of the paper. So, if there is a current in the, suppose there is a magnetic field produced somehow instantaneously like this, then what will happen? These beam electrons which are going this way, they will turn around a little bit, and here they will turn around this way, here they will turn around this way, because the magnetic force that acts on them is Q V cross B. So, if this velocity is in the z direction, suppose this is my z direction, and this V0, this V is in the z direction, and magnetic field is perpendicular to the plane of the board of the paper. In that case, these electrons will have a tendency to bunch. And how about the electrons of the plasma coming from the opposite direction? They will have a tendency to bunch in other regions. Like this electron will try to move in the downward direction, and well, just like if the electron were here, this electron, because magnetic field is here, then this electron will tend to go in the opposite direction, this way, and this electron which is over here, this will tend to go in this direction. Means the bunching of beam electrons, and these are plasma electrons, they will bunch in different regions. The regions from where the beam electrons are moving out, in those regions the plasma electrons will bunch, rather I think I have not drawn this properly, they will bunch in those, actually they should bunch in these regions, the plasma electrons will bunch here and beam electrons will bunch in these regions. This is what will happen, this is what should happen. And when there is no overlap of the beam current and plasma current, then situation becomes very similar to this, and in intermediate regions magnetic fields are reinforced. So, the magnetic perturbation will grow. So, as the magnetic perturbation grows, more and more filamentation of plasma current and beam current will take place, and that will give rise to growth of the instability. For the generation of magnetic field, primarily we require a magnetic net current in the system. Initially there is no net current if there is a 100% overlap and cancellation of beam current with plasma current. But with the arrival of a small magnetic perturbation, the current filaments, electron currents in one location and beam current in different location, and that gives rise to enhancement of magnetic field and hence the growth of the perturbation. This is primarily the mechanism of Weibel instability. I would like to consider a situation like this. for the sake of instability analysis, it is always useful to resort to a simple geometry. I will consider the case when beam density and plasma density are equal. This is the electron density of plasma electrons, density of plasma electrons, and this is the density of beam electrons. So, we will consider a situation for the sake of mathematical simplicity that the two densities are equal and the two particles are moving in opposite direction. This is moving with drift velocity v0 in the positive z direction, and this is beam and this is plasma. So, beam electrons are moving with drift velocity v0 z, velocity of the beam, and drift velocity of plasma electrons is v0 z with a negative sign. Plasma electron drift. This is the equilibrium I consider. There is no DC magnetic field in the system, there is no, so static magnetic field is not there in the system, there is no electric field in equilibrium, so E static is also 0. So, this equilibrium I would like to perturb by an electromagnetic wave. Now, let us physically understand what kind of perturbation we are looking for. We are having a stream of counter streaming particles this is the beam stream, this is the plasma electron stream. I want the magnetic field to be perturbation to be perpendicular to the direction of propagation, so that V cross B force acts on the particles. So, suppose my perturbation is in this direction. Let me, for the sake of specificness, this is my z direction and let this be my x direction. So, I want to consider magnetic field B of the perturbation to be parallel to y axis. If you are considering an electromagnetic wave travelling along the x direction, because k vector of this wave I want to be to be a function of x. So, though B itself is parallel to y, but the value of B varies with x, means B depends on x, though its direction is y. In such a situation, if you examine the Maxwell's equation, the electric field has to be perpendicular to B and k, and hence that should be in the z direction. So, perturbed electric field of this perturbation is parallel to z, and we shall discover that other components of electric field are really unconnected to z component of electric fields and they do not grow. So, this is the only perturbation. So, it is a simple situation, means consider as if some electromagnetic wave is travelling perpendicular to these beams. Well, we will see what should be the frequency, is it 0 or finite or what for a given wave number of this wave. Now, physically what is happening, that the magnetic field is like this. So, these beam electrons will turn around the lines of force, will try to move, deviate from their own path, and they will try to converge somewhere and get rarefied somewhere else. So, this magnetic field should cause a perturbation or in particle path, and hence density compression, a rarefaction somewhere. In the process, a current is created, in beam current gets filamented in some regions, and plasma currents is filamented in a different way because of the reversal in the velocity of those particles, and then the instability will grow. So, let me consider the perturbation in the system, let the electric field of the perturbation is polarized in the z direction and amplitude is suppose A exponential minus I omega t minus say kx. This is the kind of perturbation I want to consider. How about the magnetic field? If you examine the Maxwell equation, third Maxwell equation, curl of E, that is equal to minus delta B by delta T. If electric field varies with T and x in such a fashion, then B field should also vary in the same way, so that this equation is satisfied at all times and all values of x. So, if I take the variation of B with time like this, I can replace delta delta t by minus I omega, and this becomes I omega into B. B is mu 0 H, where mu 0 is the free space permeability of the plasma, free space permeability. For plasmas, permeability remains the same as in free space. Now, this del operator I can replace by Ik x cap. So, this becomes Ik cross E is equal to I omega mu 0 H or mu 0 B, whatever, or mu or B. So, what you get is B, you can call this as I omega B also. So, B is equal to K cross E upon omega. I would like to allow omega to be complex so that the wave amplitude can grow. In that case, A is not the amplitude of the wave, it is a quantity which is independent of space and time, but some term because of complex nature of omega will join this term here, then that will be called as the amplitude of the wave. So, I would like to examine in what condition omega acquires a complex character and omega acquires a positive imaginary part, so that the net amplitude of perturbation grows. When amplitude of E grows, obviously B field will also grow. I would like to see this happens. In order to examine the character of or evolution of this wave, we need to obtain the current density, because we need to solve the Maxwell's equation, fourth Maxwell equation, and for that I need to obtain the particle response to this perturbation. Now, I would like to write down the equation of motion for electrons. I will localize my or rather limit my discussion to non-relativistic case, so that the physics becomes rather clear. So, I am considering a non-relativistic equation of motion, which is m, mass of the charged particle, into delta V by delta T plus V dot del V is equal to minus E minus E V cross B. Well, when there was no perturbation, no electric field was there, no velocity was there, no magnetic field was there, in that case the particle velocity was V0 z cap. This is the beam response. Well, if I want to write this equation for the beam electrons, then I will put a subscript B here, then this is called B here, B there, B here and B there. Minus E is the charge of an electron. So, the beam velocity was V0B when these fields were not there. In the presence of these fields, we say that this becomes is modified by a quantity called V1B. This is the modification. I will substitute this in this equation and linearize this equation. Linearize means ignore the product of perturbed quantity V1B with itself or with the magnetic field, because I will treat this B and E as perturbations. I substitute this in this equation, then and neglect the products of perturbed quantities, then this equation becomes delta V1b by delta T plus V0b outside dot del of V1b is equal to minus E upon m minus E upon m. I am dividing this equation by mass. Now, V cross B is only V0b cross B, that comes in there. V1 times B, that product has been ignored, being the product of two perturbed quantities. Similarly, here V1b and V1b product has been ignored, and there is no V0b inside the del operator, because V0b is a constant, and when you take del operator it will be 0. So, this is the linearized equation. Let me write down the z component of this equation. The z component of this equation will give you minus I omega from here, because I am replacing delta t by minus I omega. The reason is that E and B, this right hand side is the driver, is the source, which has a dependence on space time like exponential minus I omega t minus kx. It means that my response also in the quasi steady state should have similar dependence on time and space. So, whenever V1b varies with time and space like this, I can replace delta t by minus I omega. So, it becomes this one, and del operator by ikx rather. But please remember, ikx, if I put here, ikx turns out to be, well, let me write down, plus V0b for this dot ikx cap, this is the k vector, del operator is this much, into V1b is equal to z component right hand side would be minus E Ez upon m. Now, this term V0b is in the z direction. So, this term does not contribute to z component, this is all. Sorry, I am writing z component, so please I should remove this vector sign here, vector sign there, write z component here. This is what I want to do. So, this is the z component of the equation. V0b is in the z direction, this is the x cap is in the x direction, this also becomes 0. So, what you get is V1b z turns out to be is equal to E Ez upon m I omega. I would also like to write down the x component of this equation. The reason is V0b is in the z direction, b is in the y direction, so this has x component. So, V1b is expected to have a x component. So, let me write down the x component of this equation. Delta t of V1b x plus V0b dot del, well, when I put x component I should remove this vector sign, I am sorry, into V1b x is equal to, there is no electric force in the x direction because electric field is in the z direction. So, the V cross B term gives you minus E upon m, V cross B, I want x component. So, that will be V y B z, which is 0, minus V 0 z, so which is V 0 b in the z direction, and b in the y direction, b in the y direction, let me write. And this B y I can really write in terms of electric field, because we have already seen that B is equal to K cross E upon omega. K is in the x direction, E is in the z direction. So, x cross z is minus y cap K upon omega into E z. Just I substitute this in here and replace this delta delta t by minus I omega and del operated by I k x cap. So, I get minus I omega V 1 B x, this gives you plus I V 0 B dot k x cap into V 1 B x. So, I into k x cap is the value of del operator, right hand side would be equal to minus E k upon omega V 0 B into E z. This term is identically 0 because V 0 B is in the z direction. So, then when you dot this with k, it will be 0 and you will get V 1 B x so much is equal to E, well I forgot to write this m should be written there. So, you get E upon m omega and this E z is also there. So, E z upon m omega, sorry why did I write this omega? Yeah, this omega is there, one extra omega is there. So, you get k V 0 B upon omega, this extra omega, and this I will also be there. So, this is what you get. Once I have obtained the velocity components, and if you evaluate V 1 y, it will be 0. Now, current density due to the beam electrons, perturbed current density due to beam electrons is the product of charge into density into velocity. I want the perturbed quantity. So, let me write down, this is called perturbed, not the DC part, the perturbed part, that will be equal to minus E n 0 B into V 1 B minus E n 1 B into V 0 B. This is the current density. Now, the current density involves the density perturbation, and hence I should find out whether there is any density perturbation or not. Please note, your k is in the x, k was in this direction, this is your k vector, perturbation like some sort of a wave is travelling in this direction, beam is travelling in this direction. So, what is happening here, if the perturbed velocity is also in the same direction as k vector, then that will give rise to compression rarefaction of beam electrons. So, density perturbation arises because of this B 1 B x. So, I would like to evaluate the value, and that can be done. So, before I evaluate this perturbed current density, I need to solve the equation of continuity. And the equation of continuity is for the beam electrons, rate of change of density of the beam electrons plus divergence of beam density into beam perturbed velocity or beam velocity Vb is equal to 0. We write down beam density as the initial density or equilibrium density plus a perturbation, and beam velocity already we had written as V 0 B in the z direction plus a perturbed quantity. This is what we had done. Substitute these in this expression and ignore the products of n 1 with V 1, and obviously n 0 V 0 product will have divergence 0 because they are both independent of position. So, when you take divergence of this product, it will not appear here. So, what really you get here is, on substituting, the equation becomes delta n1b by delta t plus divergence of n0b v1b plus n1b v0b equal to 0. Now replace this by minus I omega and del by ik. What you get is minus I omega n1b plus ik vector, which is in the x direction, dot here n0b v1b plus n1b v0b equal to 0. This term does not contribute because k is in the x direction, v0b is in the z direction. So, this product of k with v0b will vanish, and hence these two terms survive, and they give you density perturbation is equal to n0b k dot v1b upon omega, and v1b has x component and z component because k is in the x direction. So, only x component of v1b will survive here, n0b k upon omega into v1bx. So, now let me visualize the equation for current density. The current density equation is J, perturbed current density J1 of the beam electrons is equal to minus n0b E v1b vector minus n1b E v0b vector. Let me write down its components, x component, and because v1b has x component and z component, v0b has only z component. So, both I have to retain. So, J1bx turns out to be perturbed current density due to the beam electrons is minus n0b E v1bx. This has no x components, I do not write it, and J1b z turns out to be minus n0b E v1b z component minus n1b E v0b z component. And if I substitute the value of n1b, what you get here is, actually this z component I need not write because v0b is in the z direction anyway. So, I do not have to write this z component here. This equation I can simplify a little bit, minus, well, if I put the value of v1b, this becomes minus n0b E square upon m, let me just I omega into E z. This is the value of the first term. Second term is n1b. If I substitute, then I get n0b E, one E is here and there is another E in the expression there. Let me just write in two steps. n0b into E k upon omega into v1bx into v0b. This v0b I have written here, and this is the value of E is already there, n0b k upon omega v1bx I have written, and let me put the value of v1x here as well as here. v1bx that I had obtained was So, this becomes minus N0B E, and this is E Ez upon m omega into k V0B upon I omega. The same expression I will substitute here. So, this becomes minus N0B E square upon m I omega common, and you will get Ez also common, and it turns out to be 1 plus k, 1 from V1 Bx when I put this expression here. So, k square V0 B square and 1 omega square comes, so k square upon omega square, what you get is this. That is something interesting. Please note that the beam electron perturbed current density due to the electric field in the z direction is modified by the beam velocity by this term. If the beams electrons were not moving, then this term will be 0, and this is the conventional RF conductivity into E. And interesting thing is that the beam current acquires a x component also. The electric field of the wave is in the z direction, but the beam acquires a current density in the x direction, but this depends on the particle velocity, first power. So, if I evaluate a similar quantity for plasma electrons have same density that we have assumed, same charge, same mass, but velocity is in the opposite direction. So, if I calculate the perturbed current density for the plasma electrons, I will call this J1P, its x component turns out to be exactly opposite of this, because velocity of the electron plasma is negative DC velocity. So, that gives me minus N0 E EEZ upon m omega multiplied by k V0 upon omega into I. This V0B is equal to minus V0 to be replaced. So, this is the magnitude of beam velocity, this is the magnitude of, they are equal, I am taking them to be equal, I will take V0B equal to V0 magnitude wise. So, because of the reversal in sign of velocity propagation, this term has become actually positive, and when you add the two, they will cancel out. The net current, perturbed current, is the sum of beam current density plus plasma current density, and because they are of opposite sign, they will cancel each other. So, the net current, and what about z component of current density? Because it depends on the square of velocity, they add up rather than cancelling each other. So, I would like to write down the net current density in the system J1, which is equal to J1 of the beam plus J1 of the plasma electrons, and this term has J1x total is equal to 0 because of the cancellation of beam current density to plasma electron current density, and J1 Z turns out to be additive, it becomes minus twice N0 E square upon m I omega Ez 1 plus k square V0 square by omega square, where I have taken N0B is equal to N0, V0B is equal to V0. This is an interesting situation. This is the additional term that has come up because of the beam electrons having some finite velocity, and equal velocity is being held by the plasma electrons, though in the opposite direction. Now, let us examine the consequence of this current on the in the wave equation. By wave equation, general electromagnetic wave equation can be deduced from Maxwell's equations. Curl of E equation I have already written, which is equal to minus delta B by delta T, and which was equal to I omega mu 0 H, and the last Maxwell equation is curl of H is equal to J, but actually I want J1 basically, plus delta D by delta T. For plasma, displacement current density is the same as epsilon 0 into E, and if I replace delta delta T by minus I omega, I will get this is equal to J1 minus I omega epsilon 0 into E. I should substitute for J1 from this expression, and they are coupled equations for E and H. I think before I substitute for J1, let me take curl of this equation and use curl of H from here in this equation. So, when I take curl of this equation, multiply this by curl from both sides, on both sides, and then use this equation here. So, you will get curl of E, curl of E is equal to I omega mu 0 curl of H. Use the second equation, or last equation rather, and this becomes is equal to I omega mu 0 multiplied by J1 minus I omega epsilon 0 E. It is useful to multiply epsilon 0 up and down. So, if I multiply this, divide by epsilon 0 and multiply by epsilon 0, then mu 0 epsilon 0 is called 1 upon c square. So, I can write down this equation as I omega upon c square epsilon 0 here, J1 vector, and when you take this in the interior, this becomes epsilon 0 will cancel with this is 1 upon c square. So, you get plus omega square by c square E. This is perturbed current density. This you break it, this is minus del square of E plus gradient divergence of E. Replace del operator by Ik, this gives you k square E vector plus Ik here for del and Ik for this del in the interior is equal to I omega by c square epsilon 0 j plus omega square by c square E vector. Take the z component of this equation. This k does not have any z components, this term is identically 0, and this gives you k square Ez is equal to I omega upon c square epsilon 0 J1z plus omega square by c square Ez. And J1z already we have obtained in terms of Ez. So, let me substitute, and when you substitute you get k square minus omega square by c square into Ez is equal to I omega by c square epsilon 0 into J1z. When I use the value of J1z that I had deduced, it turns out to be equal to minus omega p square upon c square into 1 plus k square V0 square upon omega square multiplied by Ez, where I have introduced a quantity omega p square which is equal to twice n0 E square upon m epsilon 0. 2 factor comes because there are the total density of electrons due to the beam plus the plasma electrons is 2 n0, n0 each species. So, this is why 2 n0 comes in here. This is the equation. Now, this equation If there was no beam, it gives you k square. If the dispersion relation you can obtain by Ez is there, cancel the Ez and you get the dispersion relation. So, the dispersion relation that you get is k square minus omega square by c square. Well, this term I can put here is equal to minus omega p square by c square 1 plus k square V0 square by omega square. What I can do? Multiply this equation by c square and this equation take the following form. I can write down this omega square minus omega p square minus k square c square. So, if I take multiply by c square, take everything on one side, you will get omega square minus omega p square minus k square c square minus omega p square k square V0 square upon omega square equal to 0. Now, multiply by omega square also, then this becomes a quadratic equation omega square. The result is it becomes omega 4 minus omega square multiplied by omega p square plus k square c square minus omega p square k square V0 square is equal to 0. Such a rich physics of current filamentation is contained in the very simple algebraic equation, and we can easily solve this to obtain omega square. The roots is equal to 1 upon 2. This is like ax square plus bx plus c equal to 0. The roots would be 1 upon 2a into minus b, which is negative of this quantity. So, becomes omega p square plus k square c square minus plus or plus minus you will write here. We will be considering only negative sign because we want omega square to be negative, so that there is a instability. So, I will consider only negative sign. Omega p square plus k square c square whole square plus 4 omega p square k square V0 square. This is called the dispersion relation. If my beam has V0 non-relativistic, it means V0 square is much less than c square. So, this is a much larger term than this. So, in that case I can carry out binomial expansion of this, and this turns out to be approximately equal to half omega p square plus k square c square minus, when I take this quantity outside, it gives me, on taking the under root, same factor omega p square plus k square c square, and then you will get within this 1 plus, when you take the under root and use binomial expansion, it becomes 2 omega p square k square V0 square upon this factor omega p square plus k square c square whole square. You may note that this first term 1 here will cancel with this entire term, and this is the only term that survives. 2 will cancel with this 2, and this becomes is equal to negative times, it is negative omega p square k square V0 square divided by omega p square plus k square c square. That is a neat expression, and if negative sign is there, then omega can be written as I times gamma, imaginary term, and gamma is then called the growth rate, and the value of gamma is equal to, just you can rewrite this as omega p V0 by c into 1 upon a factor, which will go as 1 plus omega p square upon k square c square. under root. So, growth rate is the under root of this quantity, omega p is like this. I have taken k square c square common, k square will cancel out, V0 by c you will get, and this is the expression. Very neat expression. The growth rate goes as proportional to omega p, proportional to beam velocity, and it depends on k also in this fashion. When k is 0, in that case what will happen? When k is 0, this term is very large and the growth rate is 0. And when k becomes infinitely large, very large, in that when k tends to infinity, in that case this term is 0 and this is the maximum value. So, the growth rate increases with k. Here also you can see, because if k is 0, then this term you can ignore and this is proportional to k. So, if I plot a graph here, gamma versus k here, then this will increase and we will go like this. Sorry, I made a mistake, I should not do this, this is not right. This is opposite. I think let me remove this page. I am having growth rate is equal to omega p V0 by c. I think I was not wrong, into 1 upon 1 plus omega p square upon k square c square. Sorry, I think I was right. If I want to plot this, I am plotting k here. I think interesting quantity will be kc by omega p, kc upon omega p, and growth rate here. When k is 0, this term is very large, one can be ignored, and very large in the denominator means gamma is 0. Actually this really goes like this. And at very large values of k, this term is negligible. So, growth rate tends to a value here which is omega p V0 by c, omega p V0 by c. This is the value, growth rate goes like this, and this is typically 1 is here somewhere here, this is like 2. So, what does happen? We are considering a situation, the beams and plasma electrons were travelling in the opposite direction, and you are considering the growth of a wave whose magnetic field varies in this direction, but the 0 frequency real part is 0, imaginary part of frequency is gamma. So, if I look at this expression for the electric field or magnetic field, E is equal to A exponential minus I omega t minus kx. If I put the value of omega as I gamma, then this becomes, this was in z direction, A e to the power gamma t exponential of I kx. And B field, if you calculate, B field was in the y direction, k upon omega into E. This is the value of B. You may note here, because omega is I gamma, so this is equal to y cap k upon I gamma, and this is A e to the power gamma t exponential of I kx. Now take the real part. B and E are out of phase by pi by 2 because of this I being here. That is a very interesting thing. Secondly, if you evaluate the quantity k upon gamma, because gamma is like omega p V0 by c, this is, and kc by omega, if you look at this quantity, this is much bigger than, this is quite large. Actually this turns out to be c by V0. So, this B field has much stronger influence on this mode than the electric field. This is a very strong magnet, so primarily this is a magnetic perturbation, though this has a finite Ez also, but this is primarily magnetic perturbation. This causes filamentation of the beam current. beam and travels through a plasma, current filaments are formed. You get regions of high current, beam current, then plasma current. Like if I draw by a green pen, then in between these there will be a plasma current here, then there will be a beam current here, and then there will be a plasma current in between. This kind of situation is created. So you have created filamentation of plasma current as well as beam current, and this instability has a typical wavelength of the order of C by omega p, and which is quite a small wavelength. So this produces fluctuations, magnetic fluctuations in the plasma. Well, if you include some other effects like pressure, etc., there is a possibility that you can introduce some finite real part in frequency also, but that is not important issue. Important issue is that this magnetic field has a special structure. It produces magnetic fluctuation in space, and they could be very large. Finally, I would like to mention how this instability will saturate, because as this magnetic field grows, the beam turns around and the passage of the beam will be stopped, and this happens, instability saturates when growth rate becomes comparable to, let me write down, when this becomes comparable to, the growth rate becomes comparable to cyclotron frequency. Cyclotron frequency characterizes the electron motion. So whenever the growth rate becomes comparable to cyclotron frequency, instability saturates, and gamma, as I mentioned to you, is of the order of omega p V0 by C, and so omega C that you produce, which is equal to E B upon m. The magnetic field that is produced will correspond to a cyclotron frequency of the order of this quantity. So B is of the order of m upon E omega p V0 by C, and this could be quite large, quite high. Whenever in plasmas you are encountered with the generation of beams, you are encountered with very strong magnetic fields. Well, certainly there are other schemes of magnetic field generation, and I think I do not have time now, but I will discuss it sometime later. Thank you.